This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Welcome to Software Engineering Radio. I'm your host, Brijesh Ammanath. Today's session is about streaming databases, understanding what it is, benefits of using it, and the challenges unique to it. Our guest today is Yingjun, who is the founder of Rising Wave Labs, building the product Rising Wave, which is a distributed SQL database for stream processing. Prior to Rising Wave Labs, Yingjun was a software engineer at the Redshift team, Amazon Web Services, and a researcher at Database Group, IBM El-Madden Research Center. Yingjun, welcome to the show.
Hey, hello everyone. Thanks for having me here. I'm Yingjun. Yes, I'm the founder of Rising Wave Labs, and I'm a database guy and a stream processing guy. So really excited to join the show.
Let's start with the fundamentals. Can you provide a high-level overview of what are streaming databases?
Well, streaming database, definitely it's more about stream processing. But it's not just about a stream processing engine, it is a database system. So people may probably have already used some stream processing systems like Apache Flink or probably Spark Streaming, right? But for Rising Wave, it basically provides people with the experience of database experience for processing streaming data. In the other way, it actually allows people to process streaming data inside of database. So this is fundamentally different from the stream processing engines because streaming database actually stores the data, which means that we can essentially persist to the input and output of the stream processing jobs and then do data serving inside of the database system. So, for Rising Wave specifically, as a streaming database, it is Postgres compatible, which means that as long as you have systems that can talk to Postgres, this system is highly likely to be able to talk to Rising Wave. So which means that Rising Wave can connect to a lot of systems in the Postgres ecosystem.
Right. And what is the problem that we are trying to solve by using streaming databases?
Well, the streaming databases definitely tries to solve the stream processing problem. So what's the problem of stream processing? Well, there have already a lot of stream processing systems, right, for Apache Flink and the Spark Streaming. But I think the key problem here in today's world is that these type of systems are kind of, first, difficult to use, and second, they are not very cost efficient. So let's talk about the ease of use first. When we try to use a big data system like Spark or Flink, well, we need to think about how to write Java, right? And people may argue that these systems have already provided a Python API or probably SQL API, and then probably we can directly write SQL code or Python code. But fundamentally, you actually need to match a JVM-based system. And more importantly, the thing here is that you actually need to understand the fundamental concepts inside of this stream processing systems. Like you need to understand, what is checkpointing, what is, how we can do fault tolerance and how we can do scaling, right? You need to know how the system works internally. But in Rising Wave, people do not need to think a lot of things about this, right? Think about, if you're using Postgres, you will never need to worry about, how the Postgres process the transactions, right? And if you use Postgres, you will never need to worry about, what is checkpoint and what is failure recovery, right? You just use it and you just write SQL code. That's fundamentally different from using, let's say, system from Spark or probably Hadoop or probably Flink. Right, that's fundamentally different. And second thing here is that for cost efficiency. So when we talk about the Spark or Flink, right, and this kind of big data systems, people are talking about MapReduce, right? We try to shuffle the data, partition the data, and shuffle the data into multiple machines and ask every single machine to their local accommodation, and then we do the aggregation, right? Such kind of architecture is highly optimized for performance, which means that I can give you 10 machines. And this kind of system will achieve the best performance by running on top of these 10 machines. But what we saw in today's world is that people use cloud. So we never need to worry about how many computer nodes we can get, right? As long as we pay money, we can get as many computer nodes as we want, right? But the thing here is more about the cost efficiency. That is, how I can reduce the cost. Why that's important? Because, well, I mean, people don't really want to spend, let's say, always spend a lot of money on this data system, and they just want to provision a small amount of machine that just fits to their workload, right? If let's say that, okay, I have a small workload, I don't really want to spend 10 machines, I just want to provision one single machine for the system. And in the stream processing world, the key thing here is that the streaming workload can fluctuate. Think about it where if you're using Uber, right? Or think about it where if you're using some, let's say, LinkedIn or some other Twitter, right? The workload can fluctuate, right? Well, a lot of people will visit the website in the morning, but very few people will visit the website at midnight, right? That's a traffic, and that's why the workload can fluctuate. In the stream processing model, we really want to achieve, let's say, so-called dynamic scaling, which means that, okay, we really want to just provision as much resource as needed, right? We do not need to provision a lot of compute nodes, and we just want to provision compute node that can that can support my workload. So yeah, to summarize, Rising Waves tries to address the ease of use problem as well as the cost efficiency problem.
Right. And what's the trade-off for achieving the cost efficiency?
Well, definitely there are some trade-offs from the vendor's perspective, right? Well, because we build a Rising Wave is an open source database, and from the vendor's perspective, we actually need to spend a lot of efforts in building both the computation layer and the storage layer. It takes a long time. We actually have already spent 3 years in building a system, and now it works, and it has already been deployed in hundreds of clusters in production. But we all know that, well, it's not building one day. I mean, we have to spend a long time to build it. And second thing here is that, okay, in terms of the trade-off, we actually need, because we store data, we use the architecture called the so-called decoupled computing and storage architecture. And in this architecture, we actually need to store the data in remote object store, let's say S3. And S3 is kind of slow, right? So if we want to support latency sensitive applications like stream processing applications, then we actually need to think about, okay, how we can avoid accessing S3, right? So which means that we actually need to build pretty smart caching mechanism. But if you use so-called the computing and storage coupled architecture, you don't need to worry about that because, well, everything is stored in local machine, right? So that's a trade-off. So for big data systems like MapReduce-based systems like Hadoop, Spark, or Flink, they are actually optimized for performance. Well, for performance, probably is secondary, but we always take care of the cost efficiency. We always need to think about, okay, how we can achieve the best in terms of the cost efficiency. And that's a trade-off.
So if I understood that correctly, Rising Wave is a streaming database which uses the cloud as the data store, in this case S3, and that allows you to scale in, as per demand. And that's basically where the cost efficiency comes in. And the trade-off is obviously in being able to store data in S3, and that would be the latency or the speed of operations.
Yes. Well, I mean, if you want to store data in S3, then definitely accessing data in S3 is kind of slow, right? But here I would like to mention that, okay, use S3 as an example, right? Well, because people can store data in GCP or probably can store data in Azure, right? If they're on-prem, they actually can store data in HDFS, right? Or probably some other object store, right? We actually support all those object stores, but all these object stores have the trade-off, right? Well, they can store a lot of data without spending a lot of money, but they're kind of slow. So Rising Wave is built on top of these object stores. So we actually need to figure out, okay, how we can achieve the high performance when using such kind of object store as a storage.
Right. Taking a step back, obviously Rising Wave is close to your heart because you founded the product. You are the founder of the company. But what are the various streaming databases available in the market?
Okay, so when we talk about this thing, well, people will say, okay, streaming database is a new thing, right? Well, it's actually not, to be honest. The concept of stream processing was first invented in university, in academia. And people in academia were thinking about, okay, how we can support monitoring applications using database systems. And that's why they think about, okay, whether we can, instead of just processing batch data, whether we can process streaming data inside of the database. And then that's why they build such kind of thing called a streaming SQL and allow the database to manage streaming data. And that happened in 2002. So streaming database have already been evolved for 20 years. But at the very beginning, it was for all these for academia projects. Like I can name a few, like Stream, like Aurora, like Boreas. They are all streaming databases built in academia. And then IBM DB2 and Oracle, as well as Microsoft SQL Server, all incorporate the concept of stream processing into their database systems. So I think where they actually have the product for like Microsoft Streaming Insight, it is essentially a streaming database. But people talk a lot about a stream processing engine like Spark Streaming, like Samza, like Flink. I think all these systems were inspired by MapReduce, right? Which was a paper published by Google in 2004. And what they try to address is that whether I can process streaming data in big scale, right? I probably really want to process the streaming data in, let's say, using 1,000 machines, right? 100 machines or 1,000 machines, right? And they do not really want to manage storage, so they build such kind of things. But because of the cloud and because of the all kinds of the reasons, right? People come back and say that, okay, look, well, I probably really want to have a system that provides a simpler UI or simpler interface, or I can use a database system to process streaming data. So people just come back and build a system called, I think for one of the famous systems, it's called a Pipeline DB. And Pipeline DB, it essentially provides a plugin for Postgres, and which allows users to directly process streaming data inside of the Postgres. And that's Pipeline DB. And another notable system I would like to mention is KSQLDB. KSQLDB is actually a database built on top of Kafka. That is, if you are a Kafka user, you can actually directly use KSQLDB to process your Kafka data using SQL. And that's another pretty famous streaming database systems. And there are some others like Materialize. And recently I heard of some other streaming database was invented, but definitely RisingWave is among them. Yeah, it's one of the probably best, in my opinion, it's definitely one of the best streaming databases nowadays. Yeah.
Absolutely. Considering it's quite old, right? I didn't realize that streaming databases were that old. But do you remember any use cases or any stories where your users or clients have migrated from a traditional database to a streaming database?
So if we talk about the users, then we actually saw two types of users. One type is from the big data world, and the other type is from the database world. So from the big data world, I mean that people probably use Flink or probably use Spark Streaming, and then they move to RisingWave. And in the database world, I mean that people probably use Postgres and then, or probably some other database systems, then move to RisingWave. So you're talking about the second type, right? Moving from the existing database to streaming database. So we did see that. So I can give you a few examples. One of our customers actually used Postgres initially, and they actually heavily used Postgres Materialize views to support dashboard. But the problem here is that Postgres Materialize view is not incremental. That's the first thing. And second thing here that you actually need to continuously trigger refresh to refresh your Materialize view in Postgres. I know that's where there is improvement in the Postgres community, but in many cloud products, they do not really support let's say the incremental Materialize views or probably something like auto refresh. So they think that, it's kind of difficult to use, so they move to RisingWave because RisingWave provides a really nice Materialize view that is consistent and always displays the recent data or display the fresh result. And that's one of the reasons why they move from Postgres to RisingWave. And second reason here is that they actually don't really want to maintain Materialize views or secondary indexes in their operational databases, such as, let's say, MySQL or Postgres or MongoDB. The reason here is that, if people use MySQL or Postgres, they are actually supporting their online traffic, right? Well, they are supporting their online applications. And this kind of applications consume a lot of resources, right? If you build a Materialize view inside of a operational database, then what it means that the materialized view will actually also consume a lot of resources, and it will actually compete the resource, the online traffic. So people don't really want to see that. So that's why they need to have a dedicated system to do that. And actually, we also saw some other reasons people move from the operational database to the streaming database. For example, one of our customers said that they think that their Postgres is too slow in terms of when ingesting streaming data, right? Think about, well, if you have a Kafka and then you consume data from Kafka and then ingest it into Postgres, then Postgres may not have the capability to consume so much data within just a pretty short period of time, right? But for RisingWave is actually designed for consuming streaming data from, let's say, systems like Kafka, like some Kinesis, right? So we actually can support real-time ingestion, and that's definitely a big win compared to existing database systems like Postgres and MySQL.
Right. Couple of questions basis that. For the benefit of our listeners, can you explain what a materialized view is?
Well, materialized view is definitely a pretty fundamental concept in a database system. When people send a query, people can write SQL, right? Like select star from table, right? But the problem here that if you do this kind of thing, then every time a human needs to trigger such kind of query, right? But sometimes we really want to ask a database to automatically to refresh the result for me, right? So I probably really want to see the result of a query, right? Then what I can do, I can just create a materialized view inside of a database system so that and then after you create a materialized view, then the system can automatically consume data from probably your tables or probably your upstream services or probably some other data systems, and then do the computation and then persist the data inside of materialized view. You can also think of materialized view as, let's say, a so-called a special table, a special data table inside of a database system, which can do the computation and show you the result. And that is materialized view.
Got it. You also mentioned that in some cases, Postgres is too slow in ingesting data. Can you help quantify that? What is too slow? How do we quantify that?
Okay, so in the stream processing world, there's a concept called backlog or probably back pressure. So what it means that let's say that if we maintain a Kafka, and then we want to use a Postgres to consume data from Kafka, then let's say that we have already generated the Kafka service have already generated 1,000 tuples, but for Postgres it only consumes, let's say, 100 tuples, right, at the same time. So which means that there are 200 tuples that remains in Kafka that is not consumed by Postgres. So as the time flies, we can think of like, okay, actually there are more and more data will be produced by Kafka, right? So if Postgres cannot catch up with Kafka, then it means that there is a huge backlog inside of Kafka. And we will never catch up with the latest data. And we will never see the latest result in the Postgres. So there will be a lagging inside of Kafka, inside of Postgres.
Okay, we'll move on to the next section where I want to focus on some of the architectural principles or thinking behind streaming databases. We'll start with, what are the fundamental architectural differences between a streaming database and a traditional database?
If you ask me about the difference between a streaming database and a database system, then I will have to say that for streaming database, it always do computation first and then store data. But for a database system, it always store data first and then do the computation. So I can give you an example. Let's say in a streaming database like KCDB or like RisingWave, we actually ask people to create materialized views first. And then once you create a materialized view, once new table comes in, it will be consumed by the RisingWave, will directly do computation and refresh the materialized view. And then the data will be persisted in RisingWave. Operationally, definitely, which means that the user can determine whether they want to store data or not. But in a conventional database, well, it's actually optimized for a use case where the data is first stored in the table, right? So if I insert a tuple into a table, then the tuple will be persisted. After I have already inserted a bunch of tuples, then I can send ad hoc queries like select star from T, right, to query the table inside of a database system. So that's the fundamental difference between the streaming database and the database system.
Right, got it. And how does a streaming database handle changes in the data structure or the underlying schema?
Okay, so now you're talking about the schema change, right? I think it definitely varies depending on which system you're talking about. But if you ask me about the Rising Wave, then I have to say that okay, Rising Wave does a schema change in the same way as a Postgres, which means that okay, if you want to do schema change, drop a column or probably add a new column to a table, then it will just handle the data change or the schema change in the same way as Postgres does. There's no difference at all.
Right. And you specifically called out that's the case for Rising Wave. So are there other ways for dealing with schema changes in the streaming world?
Actually, in the streaming world, when we talk about the data change, then sometimes we refer to the data change or the schema change in the upstream services, right? The reason here that for streaming database, well, one of the main data sources are actually databases, operational databases, as I just mentioned earlier, right? So let's say that you have a Postgres and MySQL, and now you have a downstream streaming database like Rising Wave to consume the data from your Postgres or MySQL. Then in this case, people can change the schema in MySQL and Postgres, right? So Rising Wave will actually detect the schema change and adapt to it. Let's say that if you add a new column in your Postgres system, Rising Wave will continually process the data, and then it will actually detect that, okay, there's a data change, there's a schema change in my upstream service, and then I will add a column accordingly based on my upstream services. But again, we'll have to say that that's how Rising Wave handles the schema change of the upstream services. But definitely there are some other systems, streaming databases, and which actually do not really support schema change. But if they want to support schema change, then I think they likely support in a schema change in the same way as Rising Wave does.
Right. How is low latency achieved in a streaming database?
Well, low latency is achieved by using incremental computation. That's also a fundamental part between the streaming database and the conventional database system. In a conventional database system, if you issue a query like a select star from T or select const star from T, right? You actually do full computation, which means you will actually need to scan the entire table and then do the computation and show the result to the users, right? But for Rising Wave and other streaming databases, if you define a materialized view like create materialized view as select const star from T, then this kind of streaming databases will always do incremental computation, which means that every time a new tuple comes in and is consumed by the streaming database, it will modify the result by just applying a delta to the existing result. It will not do the computation from scratch. It will not do that. So if we do incremental computation, then it means that we only need to care about the new data, right? We do not need to care a lot about the historical data, right? Because for the data, the result has already been there, right? So if we only need to deal with, let's say, a small amount of data, small amount of newly inserted data, definitely we can do the computation in very low latency.
Right. And the way you know that it's new data is by storing state. And because it's a database, you're able to do that.
I know that case. Okay, so there are definitely multiple ways to detect whether it's a new data based on the database. For example, I used to work in Redshift, and the Redshift detects the new data by scanning a table and identify, okay, where the new data is. But for Rising Wave, it detects the new data differently. Because Rising Wave will directly consume data from upstream services, the newly inserted data will actually be buffered by Rising Wave. So that Rising Wave will essentially know which new data has already been inserted, or probably which new data change, let's say delete or update, will need to be handled by Rising Wave. So actually it detects that this is kind of a new data or new notifications using buffers in Rising Wave.
And while we are talking about latency, is there a sliding scale of latency which drives the choice of database, or rather the processing choice? So, at one end of the spectrum, you would have a requirement that, you need the data to be refreshed or to be updated only, at the end of the day. And that's why you have the batch processing. What does that scale look like, and where does streaming databases fit in that sliding scale?
Yeah, So that's a definitely great question. So in many use cases, people probably do not really care about the latency, right? Well, people do not really care about the freshness. Let's say that okay, if I want to do financial reporting, right? People do financial reporting monthly, right? Or probably even quarterly. They do not need to see fresh results, right? If I make some changes, well, I purchase some new product. I probably do not need to do not show this purchase in my report instantly, right? So I can just show this kind of change, well, in my monthly report or quarterly report. And in this case, people do not really care about the latency, right? Well, people do not really care about the freshness. And in machine learning, I mean, some people also do not really care about the freshness, right? Well, I can probably use last year's data to train a data model, right? For sure, I can do that. But definitely there are a lot of use cases where the freshness is required. So I can give you a couple of examples. One is let's say Uber, right? Well, I mean, Uber is definitely a great example, right? Well, if I want to call a taxi in Uber, then I definitely really want to have someone to take my order, right? Instantly, right? I don't really want to say that, okay, I want to grab a Uber, but well, it takes me an hour to grab a taxi, right? So it's definitely not a very good user experience. And there are many other use cases like stock dashboarding, right? Well, if I want to show my show the changes in the stock market, I don't really want to just show people the last day's results, right? I definitely want to show the result of the stock market within the last 1 minute or probably even 1 second, right? So I don't really want to see any lagging there, right? And definitely there are some other pretty interesting use cases like manufacturing. We actually have a pretty big manufacturing customer who produces the motherboard, electronic device. They actually have a lot of factories across the world. And what happened previously was that before introducing stream processing into a company was that okay, they actually need to make phone calls. I mean, that was probably 10 years ago. And they actually need to make phone calls to directly talk to the people in the factory and check what happened. They make such kind of phone call every 4 or 6 hours to check the status. But they found that, no, it doesn't really work. The reason here that, I really want to see the latest status, right? Let's say that, if there's some anomaly occurred in one factory, then I probably really want to pause the entire pipeline, right? Well, pause the production pipeline, right? Because I want to check, whether there's some anomaly or some misfunction, right? Or malfunction, right? So, yeah, and then use the stream processing system. First, actually pipeline DB, and then they moved to some other systems there, and then recently moved to RisingWave. And once they adopted from the streaming databases, well, what changed to them is that they actually can just sit in the office and then see the dashboard and to see whether there's some anomaly occurred within the last few seconds. So that's how stream processing changes work, and how the streaming device specifically help them to better manage their product line.
So if I try to quantify that, what we're saying is if the requirement is to be able to process data from seconds to minutes, you would look at streaming databases. And if it's more than that, say an hourly or a daily job, that would be most probably batch. What about use cases where you want to process your data in nanoseconds or milliseconds? Is that something which would still be a streaming database use case?
For nanoseconds or probably microseconds, we actually see some company do that. Well, that is trading firm. Trading firms really want to process, do transactions, right? So within, let's say, nanoseconds or microseconds. But I don't really think that's a pretty good use case for streaming database. Because for streaming database, well, it's probably good for hand supporting applications that require, let's say, milliseconds. It will work, but for nanoseconds, well, I think I would suggest to directly, build your own system. That's how all these trading firms do. Actually, all these trading firms have their own specialized trading platform to process the trading data, right? Well, all the stock data in microseconds. But we do see that many trading firms actually also adopt RisingWave. We have several clients in the trading world. What they do is that they actually use RisingWave to monitor the stock market. For them, they really want to see whether there's some significant changes over the last probably few seconds or probably last 1 minute, right? They also want to track, how many transactions they have already done within the last seconds or within the last few seconds or within the last 1 minute, right? They do not need to build a specialized system for this kind of applications. But they do not really want to use a batch system. So they choose to use, let's say, the streaming database.
Okay. Yeah. So for high frequency trading applications, you've seen firms use their own custom application, whereas for tracking the stocks and other use cases like Uber, stock prices, manufacturing, that's where streaming databases usually excel in.
Yes, that's right.
Moving on to the next section, which is around data ingestion and processing. Well, what are the common protocols or methods used in data ingestion?
For data ingestion, we typically ingest the data from Kafka and all the messaging queues or CDC, the database CDC. So for Kafka, well, it's kind of like natural because, the Kafka always store the streaming data. So, but for RisingWave and or for some other streaming databases, well, they can directly consume the streaming database from Kafka or from messaging queue. And the other type is the CDC, the database CDC, or the change log of the database system. So for CDC, people use CDC because they think that they really want to directly consume data from their databases. Let's say that if we have let's say Postgres or MySQL, I really want to capture the data change and then consume these data changes into RisingWave, right? So RisingWave can do that, and we do that tool called Debezium, which is a tool specifically designed for CDC, database CDC.
Right. And are there any specific techniques for handling high volume of data?
If we want to handle high volume of data, then I would like to say that we definitely want to parallelize the data consumption. So, in RisingWave, what we do is that we can actually create multiple data ingestion sources, and these sources will listen to the upstream services and then consume data in parallel. Because if you just use one thread to process kind of the data from all these data sources, then it won't work, right? Because there may be a lot of data, right? So to allow RisingWave to consume data, large volume data from upstream services, then definitely we really want to parallelize the system. And we actually support distribution or distributing the data ingestion in different machines, and definitely also works.
I've heard the term data connectors. What are they, and what is the role they play in data quality and consistency?
Okay, so actually different systems may use different connectors, right? If you talk about data warehouses like Snowflake and Redshift, they actually have their own connector. I don't know the fundamental technology of their systems, how they build the data connector. I don't know that part, but they actually have their own connector. Like, let's say in Snowflake, they actually have a project called Snowpipe, which allows people to do streaming ingestion directly from different systems into Snowflake. But in streaming databases like RisingWave, probably KSQLDB, I'm not sure about that, but yeah, let's say inside of streaming databases, then typically we can consume data from messaging queues directly, let's say Kafka, let's say Kinesis, right? Because in Kafka, they actually have Kafka connector, right? We do not need to manage the connectors on our own, right? But if you want to consume data from, let's say, database systems like MySQL and Postgres, streaming databases typically use Debezium, a CDC tool that allows people to directly capture the data changes from the upstream database services.
Okay. And as real-time data enrichment handled, how do you manage to do that?
Data enrichment. Well, there were actually two types of data enrichment. One thing here that is kind of simple, that is probably do some basic transformation, right? Data transformation, like filtering, like aggregation, and like probably projection, right? So that's kind of basic data enrichment. I think for all kinds of streaming databases like, KSQLDB, RisingWave, PipelineDB, it can be done easily because these kind of jobs or probably queries are kind of simple, and we do not need to manage large states. But another very interesting type of data enrichment is called joins, right? Let's say that if I have multiple data sources, Kafka, MySQL, and Postgres, I really want to join the data from all these data services, right? Then how I can do that? I definitely want to do joins, right? If I want to joins, then in streaming databases, in stream processing, we actually need to manage large state, right? Large internal state. And if we want to manage large internal state, then we actually need to have, let's say, mechanisms like checkpointing and failure recovery, right? And different streaming databases deal with checkpointing and failure recovery differently. For example, in Rising Wave, we store data in S3, so that we actually rely on S3 to do all kinds of the failure recovery and checkpoint. But in some other databases, like streaming databases like KSQLDB, they actually have their local store. They actually store their data in the local machine. So they actually need to frequently do checkpointing and persist the data from the local state to the remote storage like S3. And every time a system crashes, they actually need to think about, how I can pull data from the remote storage like S3 to my local state. And that's how the streaming databases deal with the checkpoint and failure recovery. But back to the data enrichment, yes, the difficult part of data enrichment is how the streaming database can do joins. And the joins is definitely a key challenge in all streaming databases. And if we want to joins efficiently, then we need to think a lot about the failure recovery and checkpoint. And definitely people also need to think about the optimizers, because the join ordering can also affect the performance. Anyways, data enrichment is definitely a pretty challenging task if you specifically refer to joins.
I'd like to double click a bit on that particular topic about joins. Can you explain why joins are difficult in a streaming database? Maybe if you take a concrete example where you've got a data source which is coming from Kafka and another from maybe a Postgres database.
Yeah, we can actually use, let's say, the ad monetization example. Let's say that we have click stream, right? And the other one is an impression stream. Now we have two streams. One is click stream and the other one is impression stream. And as a platform, I really want to join these two data streams together because I want to see, which impression leads to which click, right? So that I can monetize the ad, right? So if I want to do such kind of drawing, right, then what I want to do is that I need to maintain two hash tables. Actually, I want to build a hash table for the impression stream and a hash table for the click stream. And every time a new tuple comes in into, let's say, the impression stream, then I need to check, whether there's a match in the hash table for the click stream. If there's a match, I know that there's one impression that to lead to one click, right? And similarly, if the new tuple comes in from the click stream, I need to check, whether there's a match in the impression stream. If there's a match, then it means that there's an impression that leads to this click, right? So I always need to maintain internal states, these two hash tables in my streaming database. Then the problem here is that how I can maintain these two hash tables, right? I probably can maintain them in memory, but the problem here is that let's say that my machine crashes. If my machine crashes, then all memory data will get lost. That's a big problem, right? Because which means that if I want to reduce such kind of computation, then I need to rebuild these two hash tables, right? Let's say that if I have let's say a 7 days data, right? If I need to process 7 days data, it means that I actually need to recompute from scratch from 7 days ago, right? From the data that was generated 7 days ago. And it will take a long time. I don't know, but probably 1 hour, probably 2 hours, probably even 1 day, right? Because that may be huge amount of data. So the thing here that we need to think about how we want to persist these hash tables, or how we want to persist these internal states. And that's a key challenge that the streaming database need to handle. And yeah, back to what I said earlier, and there are different ways. People probably just use, let's say, the local disk to persist the data and periodically do checkpointing to remote machines. But in some other systems, they may directly persist the data or persist the state in remote disk, remote SSD, not remote SSD, but remote object store. And then they use the local machine as a cache to serve as a cache to accelerate query processing.
Right. And I guess if you stored only in the local machine, the challenge is around horizontal scaling.
Yeah, so that's horizontal scaling is also quite relevant to how we want to do persistence. Because, if you want to store data in local machines, then let's say that if I want to scale from 1 machine to 3 machines, now the problem becomes that, and now we want to do scaling, then the problem becomes that, we actually need to partition the local state into, let's say, 3 pieces, and then shift these 3 pieces into the 3 machines. right? 3 newly created machines, and then to do scaling, right? So that definitely works, but you actually need to deal with, let's say, the data consistency, right? And also you need to think about, okay, there are probably some downtime during the data migration, state migration, right? But the other way, which is adopted by RationWave, that is, will directly persist the data in remote storage. If we do that, then scaling becomes that, okay, we can just create 3 new machines and ask these 3 new machines to directly access data from the remote object store. There will be no data migration. There will be no state migration, let's say, from 1 machine to 3 machines. These 3 newly created machines will directly access the remote object store to fetch the states. So yeah, these are 2 fundamentally different ways to do horizontal scaling.
Yep, makes sense. Just wanted to touch on indexing before we move into the next section. Is indexing any different in streaming databases? And how does that impact the overall query performance or data retrieval?
Well, indexing actually works in a similar way as a traditional database system. But I think for the indexing mechanism, it also varies based on what kind of streaming database you are referring to. And even in traditional databases, well, different databases may handle indexes differently, right? In some databases, their index is actually asynchronous index, which means that the index is actually not consistent with the base table. But in some databases, well, they always guarantee the consistent or the synchronous index, which means that the index always reflects the latest data. Right. So yeah, these are 2 different ways. And in streaming databases, well, definitely this is also a trade-off. In some streaming databases, well, the index is asynchronous, but in databases like RationWave, it's synchronous. But the trade-off here is that, if you want to maintain synchronous index, definitely you probably really want to have more computation resources, right? So you definitely need to consume more computation resources. Yeah, that's the trade-off.
When you say it's synchronous indexes, what you mean is basically the index gets updated as the data gets updated.
Yeah, that's right. Well, let's say that if I insert a new tuple into a base table, right, or a table in a database, right, then I should see this data in the index built on top of that table, right? I want to see that tuple. But the problem here that in some databases, well, they do not really have a consistent synchronous index. And then the index may be kind of stale. If you insert a tuple into a base table, the tuple may not be directly reflected in that index. They may be after 1 minute you will see that tuple, but there's no guarantee at all.
Got it. We'll move on to the next section, which is around security. Are there any fundamental differences in how security concerns are addressed in a streaming database compared to conventional databases or conventional security models applied?
I would say probably there's no much difference because, well, yeah, again, where security thing, where it varies based on the companies, and different companies may have different policies. For example, because some companies want to make sure that all data is encrypted, and they always use TLS to guarantee the security of the data transformation. And in streaming databases, we also, definitely we always need to obey those kind of regulations or compliance. Yeah, obey this kind of compliance. So I would say that's where there's no big difference.
How do you handle out of order events or data coming in out of order in a streaming database?
Yeah, that's a very interesting question, right? Well, because in a conventional database, people do not really care about what is out of order, right? Well, yeah, I just install data and there's no order at all, right? The conventional databases deal with transactions, but in streaming databases, we deal with orders, which means that if tuple, it may result in different results, right? It may lead to different results. So we use a technology called watermark to guarantee that even if the data comes in different orders, we do see a consistent result. Yeah, let me give you a very concrete example. Let's say that if I want to count how many sensor events there occurred within the last 10 seconds, right? If I connect RationWave with different sensors, right? Sensors may send data in different orders, right? Because of the network issues, because all kinds of issues, right? This data can be disordered. But RationWave or probably some other streaming databases, right? We always want to display the correct results to the users, even if the data is disordered, right? Then all these streaming databases actually use a concept called the watermark to process the disordered data. Basically, what the strategy is that we will actually maintain a buffer to capture the data that is ingested within a certain period of time. And if data comes late, let's say that if I want to count how many tuples occurred within the last 10 seconds, but a new tuple just come in, I probably insert this tuple back to the previous window, right? Then what will happen is that I will actually modify the result maintained by the window, right? So that's how it works. We use a mechanism called watermark.
Yeah. So what you're saying is there's a concept called as watermark, which basically allows you to say that for a certain period, it will take in all the events. So even if an event comes in late, but as long as it's within that watermark range, it will be included in that query result.
Yes.
What happens to the events which come after the watermark period?
So that event, well, I think it's kind of depending on the implementation, but in some cases, the late event will just be discarded. Yeah, basically will be ignored. But in some cases, it will probably be buffered. Yeah.
Okay, so you've got a buffer time where you wait for any events which are coming late. You still include it. If it's outside of that buffer period, you don't include it.
That's right.
Right. How do you manage data deduplication?
Yeah, in some services, there are duplicated data, right? Well, let's say that if I maintain a Kafka, right? Well, and there are some duplicated Kafka for various reasons, right? Because probably I just rebooted Kafka, right? Or probably I reset the offset, right? So basically, writing with and some other streaming databases, KSQLDB and many others, we actually will track the offset of the data. So basically, we will track, okay, which data I'm currently processing. Am I processing the 100th data, right? For 100th tuple, right? If I'm processing that, if I saw that a new tuple comes in and it is still 100th tuple, then I should discard it, right? That's how the streaming databases deal with the data deduplication.
All right. So you use something called as offset, which allows you to have a view of what has already been processed.
Oh, yeah. Yeah, I think we're software. Yeah, that's right.
Okay. So as an industry, we have moved from traditional conventional databases onto stream processing or real-time analytics. And now we've got stream databases. And I think Rising Wave is where we have got stream databases evolve into using cloud or cloud-based streaming databases. What do you see in the future? How do you see streaming databases evolve going forward?
Well, if you talk about the streaming database, the feature of streaming database, definitely I would like to say that first, is be more powerful, right? Because, as I just mentioned, very early in this talk, there was a lot of stream processing engines, right? So for newly built streaming databases, no matter whether it's KSQLDB, Materialize, Rising Wave, I believe, there is still a long way to go because, conventional streaming processing engines have already been built for probably, say, for 10 years, right? Or probably 10 plus years. And definitely we need to catch up with some functionalities like, I don't know, Java API, probably some Python API, right? All these kind of things. But in terms of the architecture, I would like to say that it's pretty interesting to see that there may be a big change in the object store. If you pay attention to reInvent this year, 2023, you will know that actually AWS actually announced this new technology called S3 Express, right? So basically what it means is that S3 can provide a single-digit millisecond latency. And that will be definitely a game changer for all the streaming databases because which means that and not just the streaming databases, I have to say that all these data systems, because that means that we can actually store data in cheap devices, object stores, and actually can allow us to handle low latency processing. Right? Because I previously mentioned that if we store data in S3, then every time we access S3, then it will probably incur pretty high latency, 100 millisecond latency, or probably 200 millisecond latency, which is not tolerable. And then we actually need to build a caching layer to guarantee that most of the requests were hitting the query and can be responded in pretty low latency. But if S3 changes word and provides a single-digit millisecond latency, then we actually can safely store data, probably all my data in S3, right? And then, we can guarantee a user that we can always guarantee the user that they can see the freshest results, right? And answer the queries in very, very low latency without incurring high expense. So definitely, I would like to say that with the hardware change, specifically the S3 Express may change the streaming database. And definitely probably the entire database world. And the third trend I would like to say is that many people talk about unified batch and stream processing, right? Which means that they probably don't really want to purchase two different systems, one for handling streaming data and the other one for handling batch data. So they are advocating for a unified system that can process both streaming data and batch data. So I do think that that's definitely a direction that streaming database should go for, right? Because, look, nowadays, streaming databases are used to process written data, right? But more data is stored inside of streaming database. Then we need to think about how we can serve this data to the users, right? Let's say that if a user really want to check the historical results, we actually don't really want to let the users to push this data into some Snowflake or probably Redshift, because that's not convenient, right? So definitely we really want to have the users to do all this batch processing and stream processing in one single system.
Isn't Spark streaming a unified framework for batch and stream processing? So are you saying that you'll see more streaming databases going in that direction?
Yeah, something like that. Well, that's a good question. In Spark, we actually have both batch and stream processing. Because for Spark, originally it's designed for batch processing. And it also has the component called Spark Streaming, which is actually designed for stream processing, right? So nowadays, people can think, can consider Spark as, let's say, a unified batch and stream processing engine, right? But definitely, I would like to remind that Spark is an engine. It's a stream processing engine. But the unified streaming and batch concept does not just exist in the engine world, or in the big data world. It also exists in the database world. Let's take Snowflake as an example, right? Well, Snowflake recently announced the Snowpipe, and they also have the live table, right? The live table is essentially a concept of the stream processing. It is because it does incremental computation, and it will refresh the results for the users, right? Automatically for the users. So I believe that the unified stream processing and batch processing will also happen in the streaming database. And I believe that with some streaming databases have already started implementing that part.
Right, got it. Okay, got it. So what we're saying is basically you've got unified batch and stream processing in the stream processing world, but not in the streaming databases world. So we will see that happening.
Yeah, we will see that happening in the streaming database world.
Okay, excellent. We have covered a lot of ground over here. We have covered the fundamentals of streaming databases. We have understood how it differs from stream processing. We have delved into the architecture and design patterns used in streaming databases. And we have also looked at some of the use cases for streaming databases. Thanks a lot for that, Yingjun. If people want to find out more about what you're up to, where can they go?
Well, they can definitely visit our official website, writingwave.com. And definitely they can also go to GitHub and check out our GitHub repository. And definitely the easiest way is to join our Slack community, the writingwave.com Slack. That's a website. And you can join our Slack community and directly pay me. And then we can talk a lot about, stream processing, streaming databases, the future of data engineering thing. Yeah.
Yingjun, thank you for coming on the show. It's been a real pleasure. This is Brijesh Amanat for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.